You're good to go.
Yeah, thank you so much. Well, it's such a pleasure to be giving the talk here. I actually think I've seen I think I've seen Eduardo in GitHub comments before, like using his packages. So it's quite fun to sort of I guess participate in this and show people what I've been working on. Yeah, so today, like you said, Matthew, I'm working on semantic data handling for Monte Carlo event generators. Specifically, what I mean by that is like the Pythia event generator in particular. And my motivation for doing this was wholly selfish. As a PhD student, I was completely new to high energy physics and phenomenology. I was actually working on nuclear fusion and stuff for my master's, so this was a very new world. And it was just quite overwhelming. There were so many different data formats and so many different, file formats and all sorts of things to sort of get my head around, lots of different APIs. So what I really wanted was something which would unify them and give me some kind of semantic control over the data. By semantic, what I mean is like related to the physics interpretations of what's going on. And so particle and vector from the scikit hep libraries were offered a lot of that physical interpretation, which was great. Particle for the PDG data, vector for momentum, but they weren't really unifying over the whole event record, which is something as sort of a newbie, I really just wanted that kind of really broad control. So I also wanted to leverage my knowledge of NumPy and Pythonic idioms. So yeah, I just wanted to create something which would give me the ability to do that. Also, coming from outside, I wanted to learn a lot about the HEP data, but more from a data-driven perspective rather than a really strong theory perspective. Of course, that's important, but like I wanted to really dig into the data, query over particle attributes, look at the ancestry data, and all of that. So the selfish part of this is that, yeah, I wanted all of those interfaces. I didn't find them where I was going out and searching for them. And I didn't want to just reinvent the wheel every single time I wrote a different script. I work in AI, so I was going to write a lot of training scripts. So the most sensible way of preventing code duplication and getting things wrong was just to publish them as packages. But the upshot of that is kind of convenient. It means that I can share them with the community now. So yeah, the solutions were to try to make the packages standalone so that you could use them in isolation from each other, but try to make them as interoperable as possible. So I utilize a lot of duck typing by using Python sort of typing and collections modules to really try to make things as standardized as possible, which would then enable like the objects to be passed around between NumPy and vanilla Python and other libraries, hopefully with relative low friction. So yeah, I had basically four overarching tasks that I wanted to solve, and so I created four packages for it. The first task was to interface with Pythia generators, with the Pythia event generator, and in theory other event generators, but I haven't implemented any others yet. To sort of map that into a Pythonic generator where you can just iterate over it with a for loop, because these exposed APIs still very much follow the C format. And I wanted the data to be exposed via NumPy arrays. And there was something which was sort of similar to that. It was numpythia, which I believe, yeah, I think maybe that's something Eduardo maintained. But yeah, I remember sort of finding out that Pythia itself exposed its Python API and then creating the wrapper for it to sort of give me what I was looking for. Once I have that data in those NumPy arrays, I wanted that way of combining it into a single event record as kind of like a heterogeneous data structure, and then querying that data structure and manipulating it. And that's what graphicle does, specifically pronounced graphical, not graphical. And the name will become clear a little bit later. Also, and this is a much more bare bones library, but I wanted to tuck away all of my visualization routines and things. I really like interactive visualizations with Plotly and stuff. And so I wanted to sort of tuck away any goodies I had there in a library. And then finally there was writing and reading efficiently from disk. And yeah, a lot of projects I'd seen had been using HDF5 to do that. The beauty and the curse of it seemed to be the flexibility. So every single implementation seemed to cook it their own way. And so, you know, it wasn't always consistently named what was momentum data, what was data identifying signal and that kind of thing, or the structure. And I did see actually one case, I believe it was the Lorentz group network, where the data actual handling was done so that the entire data set was contiguously compressed. That means like all of it compressed as a single object, but they were reading event by event when they were doing data processing. So every time they accessed an event, it would decompress and then recompress the entire 100,000 events, which would cause it to take like many hours. And so then when I re-implemented, I found it took like 5 minutes or something. So it was a big speed up. So I wanted to kind of try to standardize that a bit. This last part, actually, I've realized was maybe a bit like doing all 4 APIs is probably a bit much for a half-hour talk. So yeah, the heparchy stuff I've not actually included, but there is online documentation. Each of these is a link, by the way, to online documentation for each of the libraries. Unfortunately, there's not a lot of tutorial stuff, but I've written API references for everything, and I've tried to make them as complete as I can. And there is sort of example code in a lot of them as well. Graphicle is probably the most extensive one. So yeah, I'm being blocked by the bar here. There we go. Yeah, so graphical is probably the most extensive one. It does have some example code here. Anyway, so yeah, if you're curious, you can look through the documentation for this and for heparchy, which, as I say, I won't have time to cover today. So yeah, the features, caveats, and disclaimers. I tried to make it as efficient as possible. It's mostly leveraging NumPy. The data, wherever possible, doesn't get copied under the hood. It's mostly views on arrays and what have you. Where I wasn't able to use NumPy and SciPy recently, I've been turning to Number. And so I've just tried to make things as efficient as I can. Obviously, that's, you know, that you can never do that perfectly. And I'm sure I've made plenty of mistakes, but and also I've tried to get all of my data structures to follow Python's data model, so that you won't be reaching, hopefully, for documentation super duper often. There should be some things which feel a bit familiar to you if you're used to Python's data structures. I do, however, a lot of this is built in mind of my own use case, which is to process the data event by event, which might be a bit less efficient. I don't really use awkward arrays and stuff, which I know can crunch a bit faster if you're doing lots of events all at once. And all of this is almost exclusively just written by me for my PhD project. There may be rough edges or missing functionality. If you do find anything that you'd like changed or added, please, you know, GitHub issues, or you know, if you want to collaborate with a pull request or anything, that would be extremely welcome. But yeah, so that's the overall overview. As for the actual content, we can sort of dig in a little bit here. So to start with, I want to kind of show the data generation aspect using showerpipe. So yeah, I normally import showerpipe as ship here. And yeah, if we instantiate a PythiaGenerator, this is a wrapper around a Pythia8 generator, we can see, so we have to pass it a settings file here. This is just a standard settings file that I took from Pythia's examples folder. And we then pass that to this showerpipe.generator.PythiaGenerator object. And when we look at the developer representation, it gives us this, basically the configuration settings of this object, how we've instantiated it, but it does it in a tree format just because I think it looks slightly nicer. And it gives us where, you know, the XML data for Pythia is stored. I think that's kind of useful because it gives you an idea of where you've got Pythia installed. I personally install it with Conda. So anyway, I digress. So yeah, that gives you a PythiaGenerator object. You can then iterate through that PythiaGenerator object to get events by either calling next or by using a for loop. And so this is part of that goal of doing things in quite a Pythonic way. So here I've got it showing that, you know, the developer representation shows you the underlying PythiaEvent, and the string representation just gives you this, telling you how many particles are in your event, and this one happens to have 300. So yes, so the point of these PythiaEvent objects is that every time you iterate through the PythiaGenerator, it will give you one of these events, and you can then access the underlying data using attributes, which then expose numpy arrays. And so here you can see we've got the momentum data, and these are structured arrays. I've opted for the convention of having X, Y, Z, and energy in this order. And also I saw a lot of people using PX, PY, PZ. I think when I was early in my project and kind of my hubris, I was like, that seems silly because we already know this is momentum data, so why not just call it X, Y, Z? I now realize that Y actually is often used for rapidity, but that's kind of a historical decision I've made now. It would be silly for me to go back on it. So yes, anyway. And you can see, yes, here we've got some PDG data. These are all just, standard numpy arrays where you can access the content. The length of this generator, if you called len on it, it would give you a not implemented error because we haven't actually passed it any way of defining a length here. We've just passed it like this settings file. So this will just create an endless generator. If you do, however, pass it stuff from like external event generators like madgraph or something with a Les Houches file, then there will obviously be a fixed number of events in that Les Houches file, and you can, if you call len on the generator there, it will match the number of events which are in the Les Houches files. There's actually a fair amount of stuff you can do to manipulate Les Houches files using showerpipe. So I've got routines for tiling events and repeating them within a single Les Houches file so that you can just pass it to Pythia and have it, reshower, rehadronize those same events over and over if you want to sort of study single events or do some representation learning or stuff. And also ways you can split it up using Python iterators to sort of reduce the memory demand of loading these things into context. And I actually use that to parallelize my data generation. So I split up the Les Houches files and then have them use MPI to have them split across multiple sort of processes and generate my data in parallel. But there are lots of things you can do. I haven't included the Les Houches functionality here, but it's under a module called .lhe of showerpipe. So that's another thing to check out. So speaking of, I can show you an example of passing a Les Houches file and what you might need to do in order to do that. Once we have that data, I then want to define those sort of more semantic ways of manipulating it, those more unified ways of manipulating it. So in order to do that, I'm going to overwrite this settings file and then instantiate a new generator. This is going to take in a Les Houches file, which is colliding a gluon and a B quark to produce a top and a W. There are 10,000 events here. And you can set the seed that Pythia is using as well using this parameter here. And then, you can either use a for loop or you can use this next function built into Python to get out the events as we did before. All of these, so once we have this data out, we've got a PythiaEvent object again, but I really want to extract that data and place it into like a thin wrapper, which adds in the physics functionality. So here I have a momentum array, which will take out the momentum data. And that, it doesn't look like it's done anything impressive yet because it's, just changed the way it's represented when you sort of take a view on it. But it does have these attributes, and it's sort of a lot of it is just a subset of what vector does. The vector scikit hep library. In the early days of writing this, I did actually just wrap vector, but I've redefined these since. So we can calculate the mass of these particles. So these are the first 10 particles' masses. We can rotate the momentum. So this is rotating it in the azimuth by half pi. And that's the momentum data. So that's some of the functionality you get for free with that. Also, there's functionality with the PDG codes. So that's sort of using a PDG array. And this then wraps the PDG data and gives you access to things like the names and the charges, but also as numpy arrays. So all of these things are numpy arrays. And so we get kind of a uniform format for everything. This is something that Particle does as well from scikit-hep, but I really wanted something which would map sort of element for element each of these individual properties of the whole record, which I remember having a little issue with to begin with. So as I say, I just made an object for that. Then there's this concept of edges. Now, when Pythia or other event generators perform the showering and hadronization, they have their hard process, and the particles in the hard process, let's say maybe a top quark, might decay into a B and a W, and those then decay into more particles. The W may decay into leptons or something, and they keep on decaying and decaying down, which sort of forms a graph, a directed acyclic graph. And I really wanted to put that graph kind of first and foremost as like a primary data structure inside of my work, so that it could easily be traversed and ancestry could be analyzed. So that's what this adjacency list does. And under the hood, this is a bit of functionality which isn't included in Pythia, but is included in showerpipe. This edges attribute. This provides the COO representation of that graph. So it gives you each individual edge. And so in this graph, each edge is a particle and each node is an interaction. So it's just like basically a huge Feynman diagram. Okay, I'm going to try to speed up a little bit. I apologize. So it has an attribute leaves, which is basically like the tips of that graph. And if you compare against the final state of that showering and hadronization, you'd expect them to be the same, and they are. So this gives you another way of just analyzing that what you're doing makes sense. Graphical really shines though with composite data structures. So there are two main composite data structures. The one that I really use most is graphical itself. So it's just graphical with a capital G. Sorry if that's a bit confusing. And you can instantiate it lots of ways. You can instantiate it by passing numpy arrays, or by passing already existing objects like the momentum arrays and stuff. But you can also just instantiate it using duck typing with like something which implements the same interface as the PythiaEvent interface. So things with attributes which give you numpy arrays for each of these properties. And so that's normally what I use. So I use this class method, and you can see it gives you this record of the whole data set, and this SLC and DST. These are the edge indexes. So yes, using this, you can combine this whole record really and query it as a whole. So one thing that you can do is you can select out the hard process here, and the hard process comes from this hard mask. Now, what this hard mask is doing is it's checking against the status codes, looking at where the status codes point out that the hard process belongs. This creates a Boolean mask, which then gets mapped across the entire event record. And so by doing this, you can then look at all of the attributes of the hard process all at once, and also actually do manipulations of it. Yes, so if we actually look at this Boolean mask, it might come out a bit unexpectedly for you. This is actually because it's called a mask group. So specifically, this is actually a way of combining and nesting multiple Boolean masks together, so that you can form more complex queries, or so that you can sort of catalog different ways of masking over the data. And then when this sort of group gets passed as like a mask over a numpy array or a graphical object, it performs some aggregation over the nested masks. So in this case, it's performing an OR aggregation. So it's just anything here which is part of the hard process. So it could either be the incoming, the intermediate, the outgoing particles. Any of those are then sort of performs an OR reduction over them, and then gives you basically everything in the hard process. I hope that sort of makes sense. I know that's feels a bit woolly. The reason why this is good is it means you can then combine multiple different filters over your entire data set. So if you were, say, applying a PT cut, you wanted everything to be above a certain amount of transverse momentum, or you were applying a pseudo rapidity cut, it gives you the ability to combine those, and you can then have them as sort of separate from each other, so that you know what each individual mask is doing, but ultimately you can pass it around as a single subscript. And you can sort of access that directly, so you can sort of say, oh, I just want to select the outgoing particles here, or you can create subsets as well of the mask groups that you originally had by passing it a list with multiple keys. So yes, this is mask groups. I'm sorry, that was a bit of a flying introduction, but they really also come into their own as well for representing the hierarchical structure of the event. So of course, events, in this particular event, we have a W being produced and a top being produced, and these then decay into electrons, neutrinos, and then the top decays into a W and a B, which in this case is turning into quarks, and what this is doing, this is a particular routine from the select module of graphical, and this is giving masks over the descendants of each of these individual partons. So this directed acyclic graph, we can locate the particles in the record and then sweep through all of the descendants of that record to come up with a way of selecting them out, and that enables sort of fancy ways of reconstructing. Now I'm running quite low on time. I'm very sorry. So what I'll do is I'm going to jump ahead so I can actually show you what that structure looks like. So Kaleidoscope is my visualization library, and using Kaleidoscope, we have a function called showerDAG. That's shower directed acyclic graph, and we can then view this hard process and sort of look at the entire event as a single graph. And so here's where the start is. It shows you that the two protons are coming out of the collision, and highlighted here are those we pass those masks which identify where the partons are, and then follow down the descendants, and it's colored each one individually, right? So here we can see we've got a top, and the top splits into a W plus and a B. And so here we follow the W plus, and we can see the W plus decays into quarks and then recombines and sort of, yeah, hadronizes here. And we can see then all of the final state particles, and those have all been labeled here. The same thing here, we've got the B being produced, and we can see how the B needs to pull in background in order to annihilate its color. And then it's hadronized here as well. So yeah, that's one offering of Kaleidoscope and using graphical. You can also, and for some reason it doesn't like the zooming in very much for these particular visualizations, but if you want to sort of get a sense of the what the scatter plots across the eta-phi plane look like, you can use a function called eta-phi scatter here, and this is just going to map that final state data across the pseudo rapidity azimuth plane. And the nice thing about this, again, is it's interactive. You can sort of remove the background, zoom in a bit, have a look at different data. In terms of the actual clustering, so there is a rather sophisticated way of clustering that I've introduced, which traverses that directed acyclic graph and analyzes color data and momentum data to line things up as much as possible with the hard partons, and also remove everything that's not a descendant of the hard parton, because when they get hadronized, the ancestry does get a bit complicated. because they pull in background from. So in order to sort of like weed that out, I sort of do analysis on color and momentum, and that's all wrapped up in this function called clusters. And this will then give us out masks on the final state data to tell us how we can reconstruct each individual part of the hard process. And so this is what the output we get when we do that. And just to finish up, I mean, I'm sorry, I've really rushed this last part, but just to finish up, it's got Kaleidoscope has histogramming routines which enable sort of fixed memory histograms. I was finding it annoying to have to come up with these bigger and bigger arrays to track when I was analyzing more and more events. So I created a fixed memory histogram system. So here, this is a sort of an example. It's a fairly complicated use case example of looping through. So this is generating an event, one event at a time. It's then converting it into one of these data structures, which combines the whole record. It then clusters it using my sort of Monte Carlo truth topological strategy. And then it sort of pulls out the momentum of the tops in this particular case in the event, pulls out the constituent momenta of all of those, sums them up, and then computes the mass for each of them and updates the histogram. And we can see we get a fairly nice reconstruction here if we do that. We can then analyze whether the reconstruction is, unfortunately, oh no. Well, so this, I can tell you, I did this myself a moment ago, and it gives about 172.5 and about 3. So this output here, this hist to BW params, this tells you what the Bright-Wigner parameters would be. So this would have been the sort of central point here, which would have said 172.5, which isn't too bad because the input from Pythia is 173. And it predicts the mass is not the mass, the width is 3, which is actually a bit too big. It should be 1.5. So it's not a perfect approach, but it's at least maybe a bit better than using anti-KT and taggers. So yes, I'm sorry that was a very flying introduction to things, but yeah, that's all I have, and I think I'm just out of time. I probably don't have any time for questions, I suppose.
Thanks very much. I think we probably have time for at least one question before going to the next talk. So yeah, thanks for the nice talk. I see that Jim has his hand raised, so maybe we can go to him.
Yeah, if anyone else has a go ahead also. But main thing I want to say is this is an amazing set of tools, and certainly in terms of its comprehensiveness, and you're really covering a whole ecosystem here. But we should talk about integrating this more with the PyThiaEvent ecosystem, because it could be even stronger. And I'm not just talking about awkward arrays, because that's a major refactoring. Even in the event by event point of view, using only numpy arrays. This could benefit from, well, particle, as you mentioned. I think that whatever changes are needed in particle, we could talk about that. But also vector. You've got your own Lorentz vectors, and we can share code on that. And histogram. You've got your own histograms. And for saving hep data into HDF5 files, this would be the 4th format defined within HDF5, and you know, we've been trying to like corral these into fewer.
Yeah, I mean, absolutely, I would love to. I would love to as well. Yeah, yeah. No, I've kind of been waiting. I think to. I don't know why I've waited quite a long time, but yeah, I've sort of sequestered these away for quite a while. But I'd very much like to integrate them into a wider ecosystem.
Mm-hmm. Yeah, replacing numpy would be great, by the way.
Yeah, I mean, my hope was to have an interface for Herwig and Ariadne as well in showerpipe, but I just this is all just to sort of aid my graph neural network research for my PhD. So, this sort of doing, I decided I couldn't really do everything in that regard.
Okay, I see Eduardo has a question.
Hey, not a question really. First of all, +1. Indeed, this is fantastic. Quite a lot of things. I would make the same comment as you, Jim. There's actually there's a lot that can be integrated. I would see two aspects to it. Some of these things are already done in slightly different ways, so it's probably a matter of merging the best way for the ecosystem, because then you have something overall stronger. And I think that also some other places here where you have some very interesting ideas for something that is not yet covered. So all in all, is plus if you want. Very nice, and yeah, great that you got in touch with us and you present this at the workshop. There's certainly scope for a lot of discussion, and I look very much forward to that. So congratulations then.
Thank you very much. Yeah, I mean, yeah, as I say, I'd love to collaborate a little bit. Thank you so much.
Yeah, very much agreed. And thanks for the nice talk.